All right. Hi, everyone. Thanks so much for joining. I'm Katherine Shelminski, and I'm here with Lisa Schwartz. We're from Berkeley Lab. Welcome to the third of 5 webinars this year on the Distributed Energy Resource Interconnection Roadmap, recently published by the U.S. Department of Energy's Interconnection Innovation Exchange. The roadmap identifies a wide range of solutions to address challenges for interconnecting energy resources to distribution and sub-transmission grids. I2X advances open dialogue among diverse stakeholders on interconnection challenges, bridges knowledge gaps, and supports practical solutions. DOE's Interconnection Innovation Exchange is supporting Berkeley Lab to help advance solutions identified in the roadmap. In addition to this webinar series, we're conducting studies on interconnection timelines and costs, automation of interconnection processes, allocation of interconnection costs, and innovative technologies to evolve interconnection procedures. We're also developing a publicly available web portal to provide DER interconnection queue data from across the United States and providing training and technical assistance for state agencies. Today, our focus is on promoting economic efficiency and interconnection through the coordination of interconnection with grid planning. We have presentations by Jeff Thomas, Manager of Operations, Public Staff, Energy Division at the North Carolina Utilities Commission, Juan Martinez, the Director of Distribution System Planning at Eversource Energy, and Skylar Matson, Clean Energy Planning Lead at the New York Public Service Commission. Following presentations, we will kick off Q&A with the panelists and answer your questions and comments. We have 2 hours, so we have plenty of time for discussion. First, some housekeeping items. This meeting is being recorded. Slides for today's presentation are posted on the website. We'll be putting this link in the chat box. A recording will be posted there soon. Please enter questions for panelists at any time in the Q&A box. We'll take clarifying questions after each presentation, but hold other questions until all presentations are done. Please use the chat box to make comments at any time. Finally, if you have any questions or want to make a comment live, go to reactions and select raise hand. We'll call on you by name and unmute you to speak. The DOE I2X DER Interconnection Roadmap provides a guide of actions to take over the next 5 to 10 years to implement solutions designed to address DER interconnection challenges. The focus of this webinar, again, is increasing economic efficiency through coordinating interconnection with grid planning through the following solutions: coordinating interconnection with distribution system planning, improving coordination and data sharing between DER interconnection process and electricity system planning processes, and flexible interconnection. To learn more about I2X events and resources, you can scan the QR code in this slide here or use a link, which we will share in the chat box. Now we will turn to our presenters. We have Jeff Thomas from the North Carolina Utilities Commission. Jeff, if you can go ahead and put your video on and you can share your slides now. Thanks so much.
Okay, can you hear me all right?
Yes.
So yeah, great, thanks. Hello everyone, my name is Jeff Thomas. I'm a utilities engineer with the public staff. We're a consumer advocate here in North Carolina, one of the largest consumer advocate offices in the country. And we're separate from the commission. And just a quick disclaimer, these views are my own and not necessarily those of the public staff. So just want to briefly introduce everyone in North Carolina's situation. So we are vertically integrated in the Southeast, with the exception of a small corner of PJM in the Northeast. So this means we don't have many markets. So we purchase from markets, but we don't interact with those. We don't have a capacity or energy market. So it limits some opportunities for DER outside of working with the utility. And then we do our transmission planning almost entirely through local planning. It's called the CTPC, with some projects going through CERTIP, the regional planning, and then the utilities, 3 investor-owned utilities, and a host of cooperatives. Also, they do their own distribution planning as well. There's no independent operator. So we, for interconnection of DR, we've been on quite a journey here in North Carolina, actually, since 2020. We had a serial queue that was quite quite filled with interdependent projects, a lot of small distribution connected solar projects. And this led to a lot of interdependencies between projects, which often would hold up these interconnections or assign very large upgrades to individual projects. And so we actually, before Order 2023 came out, we transitioned to a cluster study process in 2020. And so we're just closing up we just closed our 2025 DICES cluster study. And so we run 2 of those a year, one for all resources and one specifically to accommodate a solar and storage competitive bidding process that we hold annually to meet needs identified in integrated resource plans. This transition to cluster studies has been very helpful. It's eliminated a large backlog of requests and really provided more predictable outcomes for developers and allowed integrate network upgrade costs to be assigned to multiple projects based on their impact, which has certainly helped some smaller projects get connected to the system. So as I said, we're doing these large transmission connected competitive procurements to meet our capacity needs for our growing load, but that's been largely the focus. But the utilities identify DERs as something that can help shrink the challenge to meet this large load and retiring generation. So we've been exploring working with DERs a lot more in the past few years. And there's several efforts by utilities in the state and the EMCs to coordinate generation, transmission, and distribution. I'll talk more about these in the coming slides, and in particular with a focus on ISOP. So DER and aggregation as a concept is not necessarily new to North Carolina. We already do this with some of the demand response programs, with individual thermostats, controllable thermostats and other load. But there's no independent integration. There's no market to participate in for an aggregator. So typically these are proposed through Duke or Dominion proposing individual programs for demand response in the state. PJM, as with Order 2222, appears to be on track to allow aggregated DER in the 2028-2029 base residual auction, which I think should be occurring in 2026 or 7. So that's promising for that region. And then we also have recently rolled out a new demand response program for batteries, which works through a aggregator. And so that's a pilot program. And so we'll be studying the impacts of that afterwards to see if that needs to be expanded or modified. So for distribution planning, we do quite a lot in this space. It's really accelerated over the last 5 or 7 years. And ISOP from Duke and IDP and Dominion are really promising examples. And they started out with a lot of core functionality, gathering data, AMI meters, installing health monitoring systems at substations on equipment throughout the system. And now we're really kind of getting into that second or third level of distribution planning where we're actually using that data to plan the grid and we're integrating it into system planning in a way that I'll talk about a little bit more. And then some exploration is being done by the utilities, particularly on scenario-based forecasting and automated interconnection studies, which has been gaining some traction lately. So focusing here on ISOP, so part of ISOP and using all this data and the functionality that they've gained is this circuit level load forecast. And so what's unique about these, it's not just customer load, they're also forecasting rooftop solar, electric vehicles, energy efficiency, some participation in peak shaving tariffs. And this is actually influencing planning in 2 ways. So first, it's influencing how we plan our distribution grid, identifying which circuits and substations are going to require capacity upgrades to accommodate some of these DERs. And I'll talk a little bit more about that later. But it's also modifying the load forecast that's being used in integrated resource plans. So I'm showing here on the right from Duke's last IRP, the top is the winter peak and the bottom is the summer peak. And this is showing the percent impact to that peak that's had by electric vehicles and behind the meter PV. So you can see the PV has almost no impact on the winter load, which is typically early in the morning, but the summer has got a substantial impact from PV there that helps offset the EV load. DER in the system planning, particularly demand response, is dispatchable by the model, but not selectable. And so that's something that we've been looking at, whether that should be a modification we make. And so we're kind of exploring how to further integrate these resources into system planning. One tool, one part of ISOP that's being rolled out right now is Duke's DER dispatch tool. And so what this tool is, it will provide Duke with real-time control of distributed solar and storage assets, both those that they own as well as third parties, and integrate it into their system operations, which is going to provide a much more granular control of these resources and real-time curtailment if necessary and dispatch of batteries. So this should help coordinate and provide those system benefits. And then we're also part of their ISOP and IDP is providing these locational guidance and hosting capacity maps for distribution. So I'm showing down below here on the left is Dominion's map for distribution circuits for PV load, and then on the right is Duke Energy's hosting capacity map. So this can help communities plan, and Dominion actually has also some maps for EV load and as well as residential, looking at individual substations. So this is also evolving, and now we're looking at similar maps for the transmission from Order 2023. And so addressing the solution 3.7, here in North Carolina, the North Carolina interconnection procedures govern how we interconnect, and they do differentiate between nameplate and generation export requested. And this has been helpful in some of our RFPs for solar and storage. We get a lot of solar paired with storage projects, and those can only need to seek what they need to export on net. So a 30 megawatt solar plus 10 megawatt battery doesn't have to request 40 megawatts, which can mitigate some of the transmission upgrades caused by these interconnections. And then these generators have to provide an output profile. And this is typically used in peak and valley load studies. And in many cases, particularly with solar-only resources, these resources might only be studied during the sunlight hours, which avoids any upgrades that might have been caused by expected output at night or early in the winter morning. We've also explored an ESS retrofit process. We had a pilot a few years ago when we were still kind of working with Serial that would allow an existing solar facility to add storage. And then if they were committing through operational agreements to not discharge that storage outside of solar hours, it would essentially exempt them from a new study. And if they were going to try to export during non-solar hours, only that incremental battery capacity would be studied. So that was a process that we tried for a while, but unfortunately, it rolled out around the same time COVID jumped prices, so didn't get a lot of participants there. Talking now is solution 3.8, right? So identifying the grid benefits of DER. This is consideration of benefits from DER in the interconnection process is not it's not part of the interconnection process yet. I haven't really proposed going there. That's been largely resigned to the distribution planning process. And so Duke in particular, in their last rate cases, for example, proposed a lot of capacity upgrades to the distribution system that consider the future impact of behind the meter solar and storage and other DERs. There's been fleet electrification projects that have identified clusters where corporate entities are considering or making pledges to electrify their fleets. So how can they upgrade some of those distribution areas to allow that to happen and to serve that new load? And then also we're seeing projects like this FARS Bridge microgrid project, which is a small distribution connected battery that is going to help reduce outage frequency and duration while also providing wider grid benefits. And those benefits are studied in a cost-benefit analysis. We use the Lawrence Berkeley National Laboratories ICE calculator to estimate the cost per outage, and that all feeds into the cost effectiveness of some of these projects. We also starting now to incorporate potential grid benefits more into transmission planning, which can facilitate the interconnection of and management of DERs. So 2023, Order 2023 required long-term planning that incorporated these scenarios and considered grid benefits. But we're just starting to roll that out through Duke's multi-value strategic transmission planning process, which plays out at the local level, not the regional level. And so this essentially identifies through, instead of running just one or two studies to identify overloads, this runs a wide range of plausible scenarios drawn from core portfolios and sensitivities in the recent IRP. It identifies overloads that might occur from future generation interconnections or load growth, and identifies solutions. It then narrows those solutions down through certain criteria, like how many of the distinct scenarios is a particular upgrade being identified as needed in. That adds to the robustness, as well as how much generation will this allow to interconnect. And then it will work to estimate the benefits of these projects through multiple categories, largely linked to Order 2023. And then in Dominion's territory, they also evaluate the benefits of its grid transformation plan, distribution, and transmission, and also tries to quantify those. And as a regulator, we look closely at those cost-benefit analyses as they come across when we're considering whether a particular asset is needed and prudent. This is just a map showing Duke Energy Carolinas. There are some of the results from MVST, their most recent study. So all of these projects are those that were identified in one of the studies, one of the scenarios, and then selection criteria will be applied to these to try to winnow it down to a smaller group of projects that will be proposed to the local planning process and then move forward with construction. And turning now to flexible interconnection, right? So it's been obviously a hot topic, popping up more and more lately, talking about flexible load as well. But here I'm going to focus on generation and DR. So under both the state and FERC jurisdictional interconnection process in North Carolina, there are interconnection options for flexibility available, and that would be Energy Resource Interconnection Service, or ERIS, instead of NRIS, or provisional service. So ERIS essentially allows a generator to say, I don't need firm transmission, and they are studied separately. It's determined what level of output that generator can reach in each some time period, and they're limited to that output, and then potentially dispatched down in real time if there are more local transmission constraints. But that's a relatively permanent status. They get ERIS, and that's how they operate. Provisional service is similar to ERIS, although it's a type of service that you'll get after you've had a normal study for NRIS and your transmission upgrades are perhaps beyond the date that you hope to get your project online. And provisional service will allow you to connect at potentially a lower level until those upgrades are complete. And that provisional service is being rolled out now in the NCIP at the state level. And that is actually viewed as one potential way to help these projects realize the tax credits, because if you're able to build your plant before 2030 and recognize those tax credits, but your transmission upgrades put your commercial operation out to 2030 or 2031, provisional service might be a way for you to get you in service and qualify for that tax credit and capture those benefits for ratepayers. And so we've been really hyper focused on that in particular in North Carolina. One thing we do not do in North Carolina outside of a particular situation is compensate for curtailment. So the RFPs that we run allow for both emergency curtailment as well as economic curtailment. And generators are allowed certain compensation for economic curtailment up to 5 to 10%, but there's no compensation for system emergencies. And part of this flexible interconnection, right, I talked about real-time curtailment and being able to study all these facilities. And so the DR dispatch tool and DERMS, the DR management software, rolling that out and allowing the utility to have more direct control over the DRs on the grid is really critical to that effort. And if we're going to see a lot more projects being connected under provisional or ERIS in order to achieve speed of interconnection, then we're going to need to make sure that these capabilities are robust. And so, for example, Duke is rolling this out to control third-party and utility-owned solar and storage assets that previously were only curtailed perhaps by opening the recloser. Now this tool can allow them to dial down the output by megawatt blocks. And Duke is also trying to automate this dispatch and curtailment process as well, and they expect to have some of these capabilities by 2026. And I also point out that the electric cooperatives here in North Carolina, there's approximately 32 of them, and they serve much of rural North Carolina. they purchase most of their power wholesale and manage their distribution systems. And they have really emphasized DERMS and managing a host of DRs on their grid across multiple municipality or across multiple cooperatives, from batteries to DR to EVs and PV. So lots of exciting work being done, particularly on the EMC level as well. So we've got our work cut out for it. So we're very busy here in North Carolina, trying to solve a lot of these problems associated with load growth and system planning. And some stuff we're really working on is making sure that we are really taking a close look at the non-wires alternatives. For example, we're really not seeing storage as a transmission asset as being something that is being utilized by the transmission planners and is starting to be utilized by distribution planners to kind of deploy these assets at places where they can provide great benefits. But there's some complications to using storage as a potential transmission solution in an interconnection study. We're also looking at DR aggregation and system inputs. So, for example, one area of debate in the last IRP was that DER, or demand response, was treated. It's an input. The utility loads their currently approved programs and their trajectory for growth, and then that resource is dispatched economically by the model. But some jurisdictions actually model demand response and other DRs as selectable resources. So we're experimenting with that, and the public staff has proposed some modeling in the last IRP that considered modeling certain DR programs as selectable. We're also, wanting to make sure that when we plan our distribution system and we're accounting for all this EV load and PV generation and behind the meter storage, that we're planning our distribution system taking all that into account, right? You want to make sure that your distribution transformers and conductors are sized to incorporate, what is that net load, not necessarily what is the worst possible load, and maybe there's some opportunities for efficiencies and cost savings there. Rolling out pilots like power pair is something that we agreed to a stipulation in the last integrated resource plan. And so there's currently many non-residential demand response programs and generation programs in the works. And also flexible interconnection, right? We don't have a lot of experience with this yet. We've got the options, but they have not been heavily used. But we believe that provisional and potentially ERIS will see more work in the next few years. And so we want to make sure that system operators are using the tools available to them that have been developed through these processes to make sure that we can adequately control these and integrate them into system operations. So that's it. Thank you very much for your time.
Thank you, Jeff, for this really informative and interesting presentation. All right, Lisa, do we have some clarifying questions?
Thanks for asking. One question for Jeff is that the load curve modification comment that you made wasn't clear. Are you noting simply that solar offsets growth in EV loads? Or are you talking about how the expected impact of responsive load can and should modify the shape of standard load curves?
Great. I think this question was about these slides. So this in particular is just looking at the peak. So what is the net impact? That dotted line is the net impact to the peak load. And so the utility plans their generation capacity to that peak load. And so depending on which peak load you're looking at, these DERs can have different impacts, and that's incorporated. But to your point about kind of the load curves and the shape, this DER is, this is just the peak, and these utilities in particular does consider the whole impact on load shape. So the entire behind the meter, you see industrial, commercial, and residential, those all have generator output shapes, and those do impact those classes load shapes, which can shift peaks around. An EV is the same way. There's kind of an hourly charging curve for that. And that's all incorporated into the load shape. And so obviously that can change the timing of the peak, can move the peak around, and it can change the amount of energy that's ultimately needed.
Great. A couple more here. Is the DER coordination you talked about by application of this IEEE standard 1547?
I think that's part of it, and that might influence some aspects of it, but the overall, this has been an effort that the utilities have been pursuing for some time as we've kind of noted the increasing interactions between transmission and distribution. So, so certainly a part of it, but the whole effort is driven by the benefits, the expected benefits that are there.
Okay, and a related question about DER coordination. What size systems are we talking about?
Right. So great question, because I do kind of mix the efforts we're making on the larger size projects and then the smaller size, but generally, for example, our net metering limit is 5 megawatts, and we have a lot of 5 megawatt or smaller distribution connected DERs, and so a lot of that is potentially that size limit, but try to look at when we talk about working together with this and identifying these, like in particular this slide and Morecast, that's all going to be smaller systems and integrating with those small systems and trying to model that aggregated impact in system planning, right? Because any one small DR is not going to move the needle, but if you get enough of them, they can.
All right, you're doing a great job of short answers, so I'm going to continue with some clarifying questions. Can you please elaborate and define what you mean by plausible scenarios?
Sure, great question. So when they run this model, they generally pluck from the IRP. So our last IRP had 3 core portfolios, and they represent essentially different paces of decarbonization towards our net zero carbon target by 2050, which is in current state law. And so those multiple scenarios, each of those portfolios, even though only one was approved by the commission, each of those is incorporated into the planning to say, like, well, what if we move faster? What if we move slower? So there's multiple scenarios, and a lot of that is related to how fast we meet that neutrality. But then there's other sensitivities, and there's load growth sensitivities that are typically part of the IRP. We expect higher or lower load growth. That's a part of it. And then and all of that is incorporated into these scenarios. I want to say there's probably a dozen different scenarios that they ran in MVST.
Okay, and real quick question, is the flexible interconnection offering for transmission, not distribution?
It's available for any project that connects through NCIP. So that's distribution and interconnection. Now, if you wanted to do provisional, you would have to. Most of these smaller distribution projects are not being held up by large-scale, long lead time transmission upgrades, so they don't really need the provisional at this time. It's really more applicable to these large projects that are triggering upgrades that might take 4 or 5 years to complete.
All right.
But it is available if it was needed.
Okay, we have a couple more questions, but we're going to hold until after the end of the other presentations. Thanks, Jeff.
Okay, thank you.
Thanks so much, Jeff. All right, turning now to Eversource Energy, we have Juan Martinez, Director of Distribution System Planning. Juan, you can share your slides now.
Okay. Are you able to see now?
Yes, all set.
Okay. Well, thank you for inviting me to this webinar and for holding a webinar on an exciting topic of interconnection and system planning, or at least exciting to me, a long time planner. As Catherine mentioned, my role here at Eversource is the Director of System Planning, which includes 2 teams. It includes the team that does bulk substation distribution planning, and then DER planning. And I would like to think of planners as those folks in the utility in charge of basically predicting the future without the luxury of being wrong. And that's because, those large investments that the utility do, not investment, but those large infrastructure build-outs that the utility plans 5, 10 years ahead, they actually start in the planning organizations. And the reason for that is because these are infrastructures that take, 5, 10 years, more than a decade to sometimes from initial conception onto actual build out and all the steps in between could actually take that long. And that's the reason why I said, we have to predict the future without the luxury of being wrong, because you don't want to put the infrastructures on the wrong location. With that, today I have a presentation on recent efforts from the company, mostly focused on planning for DER, specifically in the state of Massachusetts, and some of the new things we've been doing with help with our regulators and other stakeholders. Okay, before I start, a little bit about Eversource. Eversource is in New England's largest and energy delivery company. So we operate in 3 states. It's New Hampshire, Massachusetts, and Connecticut. It's about 4 million customers across the 3 states. And each state, it's basically unique. In essence, today I'm going to be focusing on some of the, like I mentioned before, some of the recent work we've done in the state of Massachusetts. The company has taken what I call a bottoms-up approach to planning. We call it integrating bottoms-up approach. And what that means is that it actually starts at the structure of the company, at the hierarchy. So within Eversource, the entire planning organization is under one umbrella. So we have transmission planning, distribution planning, DER planning, and then resiliency and reliability planning, all under one umbrella. And that's the way the company basically is structured. And our approach to planning starts basically from the bottom up. So, and that is shown here in the graph. So basically, all of the planning starts at the distribution level. So DER planning, and then load planning with the forecast, the distribution planning team and the DER planning team, they with the use of the forecast, they plan the system at the load level, at the distribution level. And then for the next 10 years, let's say, we identify constraints within the distribution system. And then to those constraints, we then identify the most cost beneficial solution, let's say, that will address that constraint, also in the 10-year planning horizon, at least at Eversource. And then those solutions and those constraints, the way we operate is then that the distribution team and the DR team passes those solutions and those constraints to the transmission planning team, who in essence will use basically the exact same information, the exact same model, and the exact same data to do a transmission level study. And then in terms, they will identify constraints at the transmission level, if any, and then identify solutions at the transmission level. So as you can see, we go from bottom up, identifying at the distribution system with everything that's coming in, the constraints, and then bubbling it up to the transmission, and at the transmission, then find solution. And this was what we call the integrated bottoms up approach for T&D planning. We've already we've been implementing this strategy for a long time now. And one example, like I mentioned before, is in the state of Massachusetts. Just as a way of background, Massachusetts has a greenhouse gas emission goal of reducing emissions by 30% by 2025, 30% by 2050, and 50% by 85% by 2050. 50% by 2030, and 30% by 2025. And then with those goals of greenhouse gas emission, we also have renewable goals, electric vehicle goals, and the standalone storage goals. So at least for our service territory, by 2050, the state goal is for approximately 9 to 10 gigawatts of solar by 2050, approximately 2.5 million electric vehicles by 2050. So, with those goals, basically, it has driven interest or demand for renewables in the state of Massachusetts. And like probably every other utility, Massachusetts itself, our service territory in Massachusetts, has unique challenges, right? And that's what I'm showing here in the diagram. So we have basically 3 areas that are unique. We have the metro area in the Metro Boston, around the Boston area, which is very high load density, very high load, low generation, not a lot of renewables, not a lot of space, right, for PV. But based on those greenhouse gas emission goals, and we have the potential for future of very high EV growth and very high sector conversion. By sector conversion, I mean gas to electric conversion. As a matter of fact, some cities within the state, especially in the metro area, have even more aggressive greenhouse gas emission goals than the state goals. So, you know, that's why I mean in the metro area, there's the future impact of high load growth based on those goals. Different from the metro area is the southeastern area of the state. In there, we have a very high demand for DER penetration, to the point that most of the areas, a lot of the areas are saturated in terms of DER. Both the transmission and the distribution system are already saturated with the amount of DER that is interconnected. And then the difference there is that the peak demand is seasonal, right? So it's mostly on off-peak times that we have those seasonal load, mostly vacation, right? Folks go there during the summer. So that's when you see the high load in the southeastern area. But during shoulder months, there's a significant amount of DER, and that's what we're seeing. And then contrary to that, you have the western part of the state with a significant potential for DER growth because there's more land available. And we're starting to see that same amount of growth that we've seen in the southeastern part. Now we're starting to see in the western part of the state. So this is the unique part of the state that we've used our integrated planning approach to basically analyze, and we've put it into practice in both the southeastern and western part of the state. I'll cover it a little bit later on that, what we have done to basically study large portions of the state, large amounts of DER basically, and how do we handle those studies in order to be more efficient. As a side note, so far, I know I say Q2 2023 there, but so far, last time I counted, is about 2.2 gigawatts of DER interconnection in the state as of 2025. So now addressing those solutions, let's say in the southeastern part and the western part, you know, what is the current status, right? So right now, the electric and the transmission system are saturated to a point where you can't interconnect more DER. So what has happened is that basically DER has stalled. Or it has stalled basically, right? And, you know, your standard cost causation approach of, you know, if a DER comes in and there's, you know, they have a negative impact on the system, then they pay for the negative impact as part of the study. That approach basically has stalled all DER growth because the cost now is prohibitive, right? We're talking now not only upgrading feeders, but we're talking substation upgrades in order to accommodate DER because we're saturated at the substation level. Not only that, we're talking transmission upgrades because we're saturated also at the transmission level, especially in the area of southeastern Massachusetts, right? So in order to address, because it is an existing, you know, would have stalled basically. DER growth has stalled, which doesn't drive with the state goals. So in order to expedite at least those DERs that are in the queue right now waiting to interconnect, the Department of Public Utilities, or our regulators, basically work with all stakeholders to establish what we call a provisional program framework, basically for planning how to interconnect the DERs that are currently in the queue, and for funding the upgrades that are needed in the electric distribution system in order to interconnect those DERs that are currently stalled in the queue. And what resulted from that is what we call the CIP, which is a capital investment project framework. And what this framework allows the utilities to do is to study DER and basically load as a holistic solution for interconnecting DER now, but to identify those benefits, right? That will the benefits for distribution customers, because part of the goal of the state is electrification as part of greenhouse gas emission reduction. So that's what we've developed. That's what we've gone through, studying now areas basically for DER growth, but at the same time accounting for the distribution benefits. And as a result of those studies, there's also an innovative approach for basically funding those upgrades. So instead of just one DR customer that basically breaks everything, pays for it, now with the new provisional program, we're allowed to group DERs, large groups of DERs, studying them together, find one holistic solution, and then develop a cost method for everybody to chip in. Instead of one DER pays, and then the rest basically connect after that, right? So that's the approach that we have taken. It has been implemented. It has been approved in the state. We have about 5, we call it group study areas, and I'll cover more of that, where we have implemented this approach. And in summary, what does this capital investment project does? That SIP framework. I think it is first in the nation approach. I don't think any other states or any other jurisdictions have done that, but it's the first in the nation approach that combine the benefits, right? If we're going to do infrastructure upgrades now to interconnect DERs that are in the queue now, that have stalled, but those upgrades will also benefit distribution customer. How do you identify the benefits so that the cost is shared? That is part of what has been identified in the framework. And then it also provides a certainty, right? So the framework for each one of those groups that were studied, those areas, it establishes a fee per kilowatt that is fixed for the next 20 years. So it gives the DR customers certainty on the cost of that installation if they apply within a certain area. And then it basically creates capability now, but that capability is also for the future customers that are coming in, right? Onto that capability that was created is also exhausted. And then eliminates free ridership. So like I mentioned before, in a cost causation approach, whoever breaks for it pays for it, right? In this approach, we group a group of customers, we do the upgrades, but even that spare capacity that's available, the future customers that are going to come in the next 20 years or until the capacity that was created is exhausted, they also pay a fee. So everybody chips in into that upgrade that was planned and developed and constructed. And that, in essence, is the benefit of this framework, right? It goes away from that cost causation and it brings everybody to the table so we can find one solution so everybody can chime in. This is a summary of the study and the work that was performed, and a summary of those groups that I mentioned that were created within the state of Massachusetts. So it's basically 5, we call it group studies. And a group study is basically we group large areas. So the number in the first column is basically the name of the group. On the second column is how many bulk distribution substations are within that group. The existing amount of DR in megawatts that is in the stage in that group, and then how much DR was studied as part of that construct, and then how much additional DR is enabled for future DRs that are connecting to that group that are going to also chip in to the cost of those upgrades. And this is just a summary table of the 5 groups that were studied, and they're currently under construction in the state of Massachusetts for interconnecting those DERs. So in general, we studied about 22 substations, about 565 megawatts of DER with a study size of about 272 of active customers that were in the queue that were mostly stalled, and an additional enable amount of about 700 megawatts, 740 megawatts of DER basically. And what the study entails, right? So each one of these studies goes through that phase. So an area was identified within the distribution system, and then the engineers, the planners consider not just the area saturated, but the actual distribution system around that area and how they connect to each other. So that area gets expanded in the way the distribution system itself is built. And then substations and associated circuits that are part of that area get grouped together, and they basically get studied together. And then for that area, we basically find a comprehensive solution that will connect all the DERs. And then because of the use of standard size equipment and the fact that if you build something new, there's still some spare capacity when you use a standard size equipment, then that additional DER is enabled, which is that one in the last column. That's the additional enabled DER. So that's the steps that we're taking. And then at the end of the distribution study, which includes, I'll cover later what it includes, but at the end of the study, basically the same, even the same models, the same results, the same data is provided to the transmission planning team. Now, the same upgrades that are planned at the substation level, at the distribution level, those are provided to the transmission planning team, who will take those upgrades, the DER growth, and then they will do the same study at the transmission level and identify if any transmission upgrades are required. And that's basically the entire cycle of the group studies that were implemented. As I mentioned, the same analysis basically is completed for the distribution, but all of these studies, even at the substation level, we perform steady state stability analysis at the transmission level, short circuit analysis at both transmission and distribution level, and then transient evaluation, EMT evaluation at the distribution and transmission level for interconnection of all the DERs both at the substation and distribution level. So, where some studies, maybe in other utilities are doing circuit level, maybe power flow and EMT, we actually had to step it up a little bit and do EMT actually at the substation level, full EMT analysis at the substation level. And then that's that entire package is the upgrade that is planned, that has been submitted, approved, and now is under construction for those 5 groups in the state of Massachusetts. What we learned from all of this, right? Forecasting is key. We have to this is not something that you can do, that you can implement without the right tools, without the right forecast. You need very high fidelity analytical tools in order to complete the analysis, including transient analysis, including power flow analysis. But it's a very detailed analysis, even though we're doing it at the substation level. And then it requires work with stakeholders, right? So none of this would have been possible if it wasn't with the close collaboration of our regulators, and then with close collaboration of the different industries and the different stakeholders. None of this would have been possible without that collaboration together, the utilities with stakeholders and regulators. And as part of that, a clear cost-benefit analysis from, between the distribution customers, the DER customer, it was part of was what was defined basically, and a clear study process, a clear process on how it's going to be implemented. That part was significant, and that part I cannot even stress enough the importance of that part. In summary, just to wrap it up, so in the state of Massachusetts, policy is accelerating the growth of both clean energy and electric demand. And that comes from state laws, that come from state goals, that come from the goals of the individual cities. As a company, we're addressing those challenges, first by collaborating with stakeholders and regulators. Second, by changing the way we do planning. We have to do more of an integrated planning that looks from top down, bottom up. And then we need enhanced tools. So the analytics, the tools have to be there in order to be, efficient at doing all this analysis. As part of the group studies of DER is a first in the nation approach for cost sharing. And I think a first in the nation approach for studying large amounts of DER in basically one solution. And as I mentioned before, integrated planning, it's for us has been a very cost-effective way of analyzing this amount of DER and basically as in an area level. And with that, I think any questions?
Thanks so much. Really interesting presentation. Lisa, I think we've had a couple of questions. I'll turn it over to you.
Yeah, we have some really good questions. I think they're not really clarifying questions, so I think we will go to the next presenter and then we'll take the more detailed questions for Juan and Skylar at that time.
Okay, sounds great. Thank you, Juan. Turning now to the New York Public Service Commission, we have Skylar Matson, Clean Energy Planning Lead. Skylar, you can share your slides now. Thanks.
All right, just checking that you can hear me.
Yes, and we can see your
Perfect.
slides.
Hi, everyone. Nice to meet you. This is Skylar Madison. I'm the Clean Energy Planning Lead at the Department of Public Service. My role is primarily around transmission and distribution planning and coordinating the policy development around those efforts. And so I want to be able to walk you through some of the things that are happening at a high level in New York State. I think I'm going to focus a little bit more on the policy side of things and kind of the overarching themes and the philosophy we work under here in New York State, in contrast to some of the more technical details that we've seen from the other presenters. So just starting out from where we are in New York State, most of what we're doing right now is driven from the CLCPA, the Climate Leadership and Community Protection Act, that was passed in 2019, which is our overarching climate policy that directed a 100% reduction in GHG emissions by 2050. And importantly, the key aspect that impacts my team is the electricity targets down at the bottom of the slide that showed we're going to a 70% renewable electricity system by 2030 and 100% zero emissions electricity by 2040. And that is a very strict target, and it gets even more strict once you read between the lines and you see that they also say in the law that there shall be no offsets, carbon capture is off the table, things like renewable natural gas seem to be off the table. And so this is a very stringent target. There are also additional technology-specific targets in the CLCPA around the solar, 6 gigawatts of distributed solar by 2025, 3 gigawatts of energy storage, 9 gigawatts of offshore wind, and a number of other individual targets that we have to plan for. So that lays out a very large plethora of targets that we have to hit, a lot of moving pieces and a lot of constraints. And so my team is kind of tasked with figuring out how this is all going to work when it hits the real world and lands on the transmission and distribution system. So this next slide kind of goes through the energy planning ecosystem in New York. This is all the proceedings that we've launched since then to address all the impacts of the CLCPA. So the first one, the big one, is the coordinated grid planning process. This was launched in response to the CLCPA to coordinate the utilities and the ISO in our territory, the New York ISO, to identify all of the transmission and distribution and generation needs that will arise in the state in order to hit that 0 by 40 target. So that's a very loaded question. There's a lot of pieces to that. And so we've actually had to peel off a few of those pieces into other proceedings, namely these next 3 proceedings, where the urgent transmission needs and other transmission needs that have been identified for technology-specific targets have been moved through the public policy transmission process that we run with the New York ISO. The 0 by 40 proceeding has taken a hard look at some of the definitions and the policy around 0 by 40, as well as an evaluation of emerging technologies, as the CGPP has started to identify some reliability issues that may arise under a renewable only scenario or in a scenario where we try to rely on only existing nuclear, wind, solar storage, and offshore wind. There's still quite a big gap, especially in New York State. This proceeding has taught me that the phrase, if New York, if you can do it here, you can do it anywhere, is exceptionally true in electricity planning. We have a little bit of everything. We have pretty much every problem you could think of for anybody in the country. So if you have any questions about your specific problems, we've probably faced it in New York. We have negative 30-degree winters. We have 100-degree summers. We have very rural areas with radial systems. We have high density urban areas with network systems. We have transmission constraints, we have distribution constraints, we have the Adirondack State Park, and we have an island, a very long one, if you may have heard of that one. So we have pretty much a little bit of everything that we have to deal with in order to optimize our system. And we've realized that we need a lot more from our emerging technologies than we've been able to get in the past. And so the 0x40 proceeding is trying to identify what actions we might have to take on things like long duration storage, nuclear, both large and small modular reactors, hydrogen, RNG, any number of other technology that we're trying to accelerate the development of in order to hit our 0x40 goals. And then this proactive planning proceeding, which I'll talk about a little bit more later, dives into the distribution analysis component of this a little bit more. We have a very active distributions system right now from both the load and the generation side. We've broken a lot of our records for solar and storage interconnections on the distribution network. We're up over 6,000, pushing 7,000 megawatts of distributed solar in New York State. We now have hundreds of megawatts of distributed storage, with a couple of more 100 megawatts along the way the rest of this year. And that's led to a lot of new considerations on the distribution network, in addition to some new problems. We're also have launched the Future of Gas proceeding. There's a lot of integration between electrification and the gas system, which I won't go into now. And then we also have the Clean Energy Standard, which focuses on the procurement of most of our renewable energy resources in New York State. So moving from the planning side of things, we're trying to figure out what do we need to do to hit our targets, down to the actual projects themselves. We've developed a number of policies over the last 10 years in the state to try to make sure that the pathway for these system beneficial resources is as smooth as possible to get them online without as much intervention. So one of the big things we've done through the Interconnection Policy Working Group and Interconnection Technical Working Groups over the last few years is the implementation of the value of DER tariff. If you've heard of the value of DER tariff, or VEDR as we call it, that has been a tremendous success through the solar and storage industry in New York State. That is a tariff we set up to be a market signal for distributed resources to be compensated through their local utility for their actual benefits to the grid. And so the value of DER tariff sets up different value streams that can be attained through different operational profiles for wind, for small wind, solar, and storage resources. And those components of the value of DER tariff are an energy market signal that maps the day-ahead energy prices from the New York ISO down to the local system into that DER tariff. We also give them compensation through a second line item on that tariff for capacity, the ICAP for each month. That's a line item in the value of DER tariff. But we also work in distribution system value. So we have a distribution relief value that is also in that tariff that the resources can capture by operating during times of distribution system overloads. And then for solar projects specifically, there's an environmental value that can be accessed by delivering zero carbon electricity to the distribution grid. So those financial mechanisms are set up on a locational and time varying basis. And so they're different in different areas of the state. And so that tariff has been one of the key policies that has directed DER development to the areas where it's needed most based on those price signals. So that's done a lot of the work for us. There has been other issues, obviously, that have arisen that we've had to identify through kind of screening methodologies, additional information through these hosting capacity maps that we've developed in New York State to kind of give even more information to help developers identify where it might be best to do their next project, because we tend to see hot spots pop up as soon as new data is published on the benefits of a system. We usually get 2 or 3 times as many projects in that area as we need to hit those goals, and it turns into kind of a run on the banks for that hosting capacity, and in some cases even leads to system needs or overloads in a certain area. So that's something that we're trying to get ahead of, and I'll go through that on the next slide. We also have the standard interconnection requirements, which is a very flexible and very advanced interconnection pathway that the utilities follow to interconnect DERs that are proposed in their system. We operate on a first come, first serve basis in New York State, where anybody can come and propose a DER anywhere in the system. They follow the standardized interconnection requirements to pass data back and forth to the utilities, and there's deadlines for each of those steps. And then at the end of that process, they're given their interconnection costs, and they can choose either to accept those or to reject them and walk away. Something that's fairly new for DERs in New York State is the New York ISO interconnection queue process for DERs. Under for Order 2222, there's been an additional movement on aggregations in New York State. Unfortunately, the market rules for DERs, especially for smaller DERs, are not very flexible and not necessarily as industry friendly as we were hoping. And so we're not expecting very much activity there, except in exceptional circumstances and very localized benefits. So for the most part in New York State, we're expecting a continued use of the utility interconnection processes, which go up to 5 megawatts in New York State. So getting back to the feedback loops between the overarching planning and this very granular interconnection process of individual resources, the primary overlap between these is how we interconnect and how we use the queue data from these interconnection processes in our planning exercises. We believe that there's not necessarily any inherent benefit to any one DER project. We're trying to incentivize things that are beneficial to the grid and are positive for stakeholders, and at least not standing in the way of projects that may not be beneficial, but not actively going out of our way to ensure any and all projects move forward. We really want to have kind of a cost minimization approach and a ratepayer impact approach that looks at the entire system as a whole through our planning studies and figures out if we're going to these targets, what is the best way to get there, and then making sure we provide the right incentives to get folks to those right locations. Both the existing and forecasted DER in New York State are built into our load forecast in all of our grid planning simulations, both in the coordinated grid planning process, the 0x40 proceeding, and the proactive planning proceeding. Primarily on those higher voltage studies, DERs are showing up as load modifiers, but they can still play a very important role, especially as we get into the mid and late 2030s, where we're expecting to have tens of thousands of megawatts of DERs in New York State, combination of solar and storage primarily. But we also have other more meaningful DERs coming along, if you call them that, with managed charging programs. We already have a couple hundred megawatts worth of batteries, essentially, signed up through that, where folks have signed up through our utilities to manage their charging through their EVs, and we're expecting orders of magnitude of growth in those programs in the coming years. We're also developing granular interconnection forecasts by using industry surveys, long-term queue data, as well as hosting capacity forecasts to build plans out for where interconnections are likely to happen in the future. And when we reach the end of that type of data, build out the system to figure out where would it be most beneficial and most impactful to have more DERs in the future. We're trying to build out a system so that the DER performance from both the operational and the interconnection system are supporting our distribution planning efforts, as opposed to being some uncontrollable kind of third-party impact that we have to kind of plan for and plan around. We're trying to incorporate that as we go forward and to be a little bit more controlled. So in terms of the planning outcomes, our distribution planning processes and the hosting capacity map development processes, they provide some really valuable insights to developers. We're publishing on a regular basis the values of different interconnections. We're publishing information on where headroom exists for their future interconnections. We're saying where the existing or new interconnections would require system upgrades. And so we're providing developers with a lot of information. We're actually trying to take that one step farther in our proactive planning proceeding, where we're going to do something similar to what Eversource is just speaking about along the way with their DER cost sharing proposal, where in the proactive planning process, we'll be discovering those DER hotspots, the ones that already exist and the ones that are coming, and having the utilities identify those and propose projects back to the commission to say, this development of this project will get us ahead of the DER development and might be much cheaper or faster or better than having each individual developer pay through the nose to get interconnected, and then have a couple of free riders, and then have a really expensive interconnection and then have free riders. And so the proactive planning proceeding is trying to incorporate proactive planning for DERs as well, to allow proactive build out of the grid to enable a smooth transition. Cost allocation is an interesting question that was also brought up previously. I think we still have some open questions there because there are a lot of socializable benefits through those types of projects, but the commission typically takes those questions on a case-by-case basis. And I think through the interconnection process, there's good basis for allocating those costs potentially in a similar way that Eversource has been doing it on a project level basis, so that the beneficiaries are paying, and it's not just a wholesale kind of subsidized by ratepayers in New York State. That's the long-term plan, but we already have a lot of new developments that we've been implementing in New York State over the last couple of years to make the interconnections of existing DERs a lot easier while we wait for these kind of broader proactive DER plans. And so I wanted to point you all back to the standardized interconnection requirements I spoke about earlier. We already have a very flexible process where individual projects can propose very specific operational profiles, and I'm thinking especially of energy storage. They can propose through their interconnection agreements specific injection or charging limits to avoid some of the worst impacts that typically show up on, discharging during low load hours or charging during peak hours. There's an appendix to our SIR process that allows them to input their preferred load shape or their preferred study shape. And as long as that is built into the interconnection agreement, they don't have to pay for the upgrades that would have arisen through irrational operation of their technology. We also have a cost sharing program that's already in existence. It's not quite as aggressive as the one in Eversource, but it does have some very similar characteristics where the utilities will study a system that might be a DER hotspot, and it might show a pretty significant upgrade for the next megawatt, but the upgrade itself might actually produce far more than 1 megawatt of upgrade. Perhaps it creates 5 or 10 megawatts of new injection capability. So in that process, the utilities have been using a cost sharing mechanism that allows the first developer to come in and pay for that cost, and then any future development that happens in that area pays a portion of that fee back to the first developer. And so that continues until the full process is paid for, and it ends up being an equivalent share across anybody who uses that component of the system. So it's a positive development because it allows development to occur in those places with potentially higher interconnection processes. But it's been a little bit, it's still been a little bit of a barrier trying to find those first movers who are willing to pay that high initial upfront interconnection cost. We've also kicked off a flexible interconnection working group. We allow some of these flexibility components in our interconnection agreements already, but we're trying to systematize it in our SIR process to just have redispatch or curtailment agreements freely available in that interconnection proceeding, as well as allowing those lower cost interconnections for, say, solar projects who may create voltage issues during 1 or 2 hours of the year, and that accounts for 50 or 60% of their total interconnection costs. They can sign over some rights to the utility to be able to redispatch or curtail them during a couple hours a year. That will then save all those costs. As you've probably heard, the theme of this for solar and storage in New York has been the control that the utilities are lacking is kind of the main driver in these higher interconnection costs. The DERs are owned by third parties and operated by third parties through either standard control algorithms according to the tariffs, or set it and forget it in terms of solar. And if they're not controlled, they could cause these issues, and the utilities aren't controlling them. And so these actions have been slowly giving a little bit more control back to the utilities, at least in the form of interconnection assurances, that has dramatically reduced the cost of some of these assets. We also allow storage to be put on site for other distributed resources like solar, and they can share their interconnection, and that has provided a lot of incentives and a lot of value. We have a lot of solar plus storage projects in New York State. One of the interesting pieces here that I wanted to know also is that ideally in the long term, we're trying to move towards more utility innovation on these developments, not just for DERs, but for new loads as well, where we can think more holistically about these grid upgrades, not just fall back on traditional planning mechanisms and traditional solutions for upgrading certain components of the electricity system, but think more holistically, especially in these DER or load hotspots, where we can find, maybe more granular results about what is causing the issue, what hours are these issues happening in that are actually causing the major grid upgrades. And maybe in some of those instances, the issue is only in a few hours a year, or it's under a few specialized circumstances. In those cases, certain technologies might actually be better. Grid enhancing technologies, for example, might be better to solve that problem and quite a bit faster than traditional system upgrades. And that would allow us to move forward and kind of utilize a more flexible approach to interconnection. And I provide one example here that we might be considering, and that is in hotspots with lots of solar, where we might be experiencing stability issues. There's the opportunity to potentially consider, instead of trying to solve the issue at every single solar project, we could potentially consider storage with grid conforming inverters at a substation, at a collector substation that's utilized by multiple solar projects. The utility would have an incentive to do so under an NWA or through some cost sharing mechanism, potentially through the proactive planning proceeding. And then those costs could be either partially socialized or shared among the beneficiary solar projects. So the key message here is that we have a lot of things going on, and all of our plans are really great. But knowing all that information and having the plans of what probably needs to go where to minimize costs still do not work unless the real projects on the ground get interconnected. I think we're in a really interesting place right now, I would say, on the wholesale market side of things in New York State, where the large scale renewable deployment, especially the actual interconnection and commissioning of those projects, have gone a lot slower than we were hoping. And so that's kind of one of the fears here on the distribution side of things as well. It's great to know that you need 2 gigawatts, but if you can only interconnect a few hundred megawatts a year, it's going to take you a long time to get to your goal. So we're trying to make sure that both sides are taken care of. We have the good plans, but we also have the good on the ground rules to actually allow those things to get interconnected. We're well on our way to getting 10 plus gigawatts of distributed solar. Like I said, we're already past 6 and moving around to 7. We have our eyes on about 2,000 megawatts of distributed storage as well. But that's coming in at the same time, and I wanted to make this point about the last presentation. Even in areas where we are currently saturated with DERs, we're expecting significant new loads from electric vehicles, heat pumps, economic development, electrification. And so what once was a DER saturated area is likely to have new load, and that might, without any system upgrades, create new capacity for DERs to come in. Coordinating between all of these things is really, really essential to minimizing ratepayer impacts. As I said before, we're not in the business of just upgrading every component of the grid just to make sure we can get another megawatt of DER. DERs are a cost-saving, beneficial technology. And as soon as you have to redo the whole grid to interconnect one of them, they've kind of lose that characteristic, and it kind of falls below that benefit cost line. And we only want to be doing things that are actually beneficial for ratepayers through our programs. And so you really have to coordinate all of these aspects, both the planning, the DER interconnection, the load, what grid upgrades are needed to make sure we're actually doing the right thing. If we incentivize too many projects in one area and it causes these massive grid upgrades, we haven't actually minimized costs. If we are looking at only interconnected DERs and we see all these system upgrade needs, but we're not including all the granular load studies showing all the loads showing up, we might be calculating far greater grid upgrade needs than actually exist. And so there's a lot of things we have to think about when we're doing these studies. Smart policy in the end, when we try to get all this data, we try to proactively build out the system. We allow for flexible interconnections so we can make best use of our existing system. All of these things can really maximize the speed and efficiency of deploying what we actually want to deploy while minimizing those costs. And so I think I'll stop it there because I've seen a lot of questions come in, and we can move on to the question portion.
Skylar, yeah, we have a lot of questions. I'm going to start with some questions for you, Skylar, and then I'm going to go back to Juan. We also have a lot of good questions for him. So first, who gets the benefits of these DER payments, and how are benefits of substation at the distribution level or transmission upgrades incorporated in the future for certain, they're just for certain customers that make use of them? So how do you do?
So it starts off with the value of DER tariff. So that tariff is based off, and the components that are paid out through that tariff are based on system benefits. So the energy payments are there because the injection from the solar facility, for example, is offsetting the need for the utility to procure additional energy. Capacity is there for the same reason. If solar is showing up during peak times, it's reducing the need to procure capacity on peak. Same thing with the distribution relief value. If it's deferring the need for additional distribution upgrades, we're paying that. So all of these are ratepayer benefits, and we are choosing to pay DERs through this tariff as opposed to paying the utility to build new poles and wires, wholesale market generation to serve these customers. And so they're really just trying to save ratepayers money by giving market signals. So the developer gets paid. So they're the one that's making the money, but the benefits are going to the entire system. In terms of the system-wide impacts, those are studied on a holistic basis statewide. And so we're trying to keep a bird's eye view on where the hot spots are and what grid upgrades are needed. And in many instances, those system level upgrades are socialized if they're going to have outsized benefits to making the ultimate goal much less expensive. But in some cases, if it's for just one DER hotspot, we plan to take more of a cost sharing approach where the beneficiary pays.
All right. And then in terms of the proactive grid upgrades, the question is, how do you anticipate cost recovery, or how do you deal with it? And that includes consideration of, prudency standards used in useful investments, if the projects are built proactively ahead of demand.
Right. And so we have a little bit of experience with this already. We've already been doing proactive grid upgrades for load for the last year or so, and we already have kind of one example of that. And so what we've done is try to make sure that we are capturing the full scope of all the projects that are in the queue that are very likely. Those projects that are in the queue have various levels of uncertainty or risk. If they've fully gone through their study and paid for their entire interconnection upgrade, but they just haven't come online yet, that's a very certain project. They have money paid out. They have some metal in the ground. But then someone who has paid for most of their upgrade, but not all the way, has a less certainty. And so as we go through these proactive planning studies, a utility may find that a 10 megawatt upgrade is necessary to enable this next tranche of DERs, but only half of them have even paid for their interconnection study report so far. That's a much lower certainty upgrade than one that is built for something where all of the DERs in the area have at least started or gotten to the second phase of their interconnection process. So we have this way of kind of thinking through, more certain or lower risk projects, as well as projects that can maybe manage that risk on their own by creating optionality or expandability into the grid upgrades themselves.
We have a couple questions related to operational agreements for a limited capacity for a combination distributed energy resource system. So one of the questions is around contingency events or worst case scenarios and enforcement, and also around the study process. So first, how do you sort of enforce it? What the limit is, and then how do you study it? I'm assuming you study it at the limit, and then that's
Yes.
it. And how do you come back and enforce it?
Yep. Until all of this stuff has happened, we were under an extremely conservative approach where the utility upfront was studying all the worst possible case scenarios, and any DER that came in had to pay upgrade costs to alleviate any potential one of those scenarios. So there was no enforcement or emergency preparedness needed because they've already built out the system to make sure none of that ever happens. We've tried to move away from that because that basically is penalizing everybody for very, very, very unlikely events. And so under these more flexible arrangements, the utility and the interconnecting customer negotiate through their interconnection agreement what their limitation should be. And in most cases, it's a physical limitation on the point of interconnection to begin with. And in more rare cases, such as the combination solar and storage projects, those are more software limited. And they have an agreement where if the utility finds out that they've been injecting more than they should have, they can have penalties.
Okay, and then related to that, are planners thinking about reserves of some sort to address some of these potential violations? I think you've already answered who pays the penalty. Just overall, anything else about how the risk is managed? I think maybe also consideration of diversity of loads and generation.
Yes, so most of the management on things like reserves or stability of the grid, all that stuff is handled separately from these processes. Our utilities do not manage that. They don't manage the ancillary services. They don't manage any of these underlying physical constraints of the grid. we operate through the New York ISO, all of the ancillary services markets. So things like stability, reserves in a given area, all of that is managed through a separate New York ISO ancillary services market. And the utilities themselves have to kind of plan out how to dispatch the system and how to set the right signals so those emergency events don't happen. And pretty much all of that is done through the interconnection process. They make sure that their systems are not going to fail no matter what in the instances of having these DERs connect. And so there's not really much else we can do right now unless we finally make it to our end goal of having distribution system platforms where these ancillary services and all the other energy products can actually be dispatched on the distribution network as well into the wholesale market, but we're not quite there yet.
That's great, thanks. I'm going to turn next to just a couple of related questions for Juan, and then I'll ask all panelists to put on their video because we're getting into a discussion among all of you. Juan, thanks for coming back. We have some questions about your very interesting capital investment project framework.
Yep.
How do you distribute the capital costs? Like what percentage is contributed by the utilities, the DER projects, ratepayers? Is it sort of proportional to relative benefits? How does that work?
So it is, so it's actually broken down by the individual group. So what happens is we study an area, and for that area, and again, I had the groups like on the chart, but for each group, there's a certain area. And then in that area, we're doing certain investments to enable the DR that's in queue. Now, the cost of those investments get broken down between, you know, the existing DRs in queue plus the future DRs in the queue as well. And then it also gets broken down into distribution customer benefits in terms of reliability and capacity benefits. So it's an all-encompassing benefits that does include, you know, distribution customer benefits, the current and future DER that are benefiting. And then it depends in the actual group. It's not a fixed value. It actually depends on the investments that have to be made on that area. And then that cost gets broken down based on the benefit that it provides to each.
Okay, great. And one more question is about how to, you know, sort of balancing the costs. So how do you balance the cost of the projects based on developers' needs with cost ratepayers bear immediately as part of the project costs? And, you know, you talked about future interconnecting customers, you know, paying the system and, you know, that being more economically efficient. And, you know, so how do you deal with that balance in terms of developers versus ratepayers?
Yeah, so the way it's structured is, you know, we'll do the investments now, let's say necessary investments to enable the DR, and then the DRs in the queue, they'll obviously pay their share, right? And then the utility will do the investments necessary, and obviously some of that will be based on distribution customers. But as the new DERs in the futures come in and make those payments, that gets deducted basically from the total cost. So at some point, if the current DERs and the future DERs will help offset all those costs of the investments now.
Great, thanks. I think we'll go to panelist discussion. If you can put your video back on, Jeff, that'd be great. And we'll come back. We do have a few more audience questions. We'll come back to those later.
I'm going to launch a quick poll for the audience while we're pulling this up. Oh. So all right, can you all see that?
Yes.
Okay, so we're going to focus first on grid coordination. So cost inefficiencies and DER interconnection arise in part as distribution system upgrades are triggered through the interconnection process. They often occur in a piecemeal fashion, which can increase costs for interconnection customers and ratepayers overall, compared to an approach that is better coordinated with grid planning processes, as our panelists have discussed today. So closer alignment of data inputs, assumptions, and process timelines between DER interconnection and long-term grid planning can help identify and deploy potential grid upgrades in a more efficient and forward-looking manner. So we have some of our polls coming in. Give it a couple of more seconds, and then I'm going to share the results. And then we can dig into some of our questions with our panelists. Okay. So the results, which you should be seeing on your screen. So does your state or utility incorporate data of DER interconnection in distribution system planning? We have 45% that answered yes, 12% that answered no, and 43% that said, I don't know. So that should be closed now. So I will turn to, thanks so much for your responses, really helpful. We'll be asking a couple of more poll questions throughout this Q&A. So we have, first up, wanted to ask all panelists, how do you coordinate interconnection for DER projects with distribution planning in your jurisdiction or your utility? You each talked about different approaches. If you want to just give a quick response on kind of your top approach that has been really effective in your state and or jurisdictions. Jeff, you want to go first?
Sure. Yeah, I was just about to. Yeah. All right. Yeah. So I talked a little bit about, but I think a lot of the current forecasting that they do in distribution, that some of the utilities do in distribution planning, is looking at propensity to have these DRs on the grid, and how do we prepare that distribution grid for that. So it's not necessarily like an actual project and then being incorporated in the distribution, but they use things like, for example, if you have a circuit that has a high concentration of solar PV already, those past interconnections might lead the Morecast model to predict a large number of additional PV, kind of with the network of the neighborhood effect. So that's incorporated a little bit, and a lot of those upgrades then are trying to be responsive to that and provide additional capacity in the areas where that type of technology might deploy. But certainly, I think we can look at that a little bit better, and we do look at the timelines for how these resources have been interconnected to kind of see how much time we have to respond to these. But yeah, that's mostly the extent of it at this time.
And for us, we primarily incorporate the DERQ data and the operational characteristics we've seen from existing resources into that distribution planning to make sure that the utilities are identifying any of those kind of shared needs that might go beyond an individual interconnection point, make sure they're raising those throughout the process so we can quickly react to those and approve some if we need to, or at least identify an area that's too much of a hot spot and start incentivizing folks to go other places.
Yeah, and from our side, so let me break it down into buckets maybe. So from the technology side, it's very important, or at least we found it very useful to standardize the technologies we use, right? So we use one common platform for, let's say, storing DR data, and one common platform for your GIS data. So that using that common platform that all the planners are going to be seeing is very useful in terms of being able to plan something holistically, right? So that's number one on the technology side. And then on the actual project development side, I think, as I mentioned before, we have, I guess we're lucky in the sense that we're integrated, right, in terms of planning. So basically, anybody that's planning for DER, at least in our group, will already have all the planned work on the same system, reliability work, capacity work, right? All of that gets incorporated in when I'm doing a study, let's say for DER, all of that gets incorporated, and we go actually beyond that. So on the group studies, we actually look at how can I develop the design that benefits more than one? How can I maybe arrange the design so that it improves reliability at the same time that I'm enabling the DER? How can I improve capacity better? So all of that gets done, when you have this combined planning process.
Thank you. That's really helpful and interesting responses here. Wanted to ask one more question on grid coordination. And this has to do with really focused on the coordination part. So how is data shared and coordinated between DER interconnection processes and distribution planning? What are the processes that have needed to be created to help facilitate more interagency coordination? And kind of how has that evolved in each of your jurisdictions? Maybe start with Yeah, Jeff, you're off mute. Go ahead.
Sure. Yeah, so I think, Dominion is their integrated distribution planning. They talk a lot about, kind of breaking down silos between teams and sharing a lot of that data. And a lot of that is just gathering it and making sure that the folks making decisions about what type of distribution upgrades are needed and when a line should be replaced in kind or potentially upgraded. They should be at least looking at the data for the DER interconnections, what's in the queue, the small generators in the queue, and planning off of that. But I think there's certainly more work that can be done, I think, on that, and kind of automating that ability to pull data from the DER queue and make sure it's being reflected. And that's often, that helps us as regulators look at the proposals for distribution planning and understand what they're for and what they're responding to.
Thank you. Let's turn to New York. Skylar, if you
Yep.
want to talk a little bit about the coordination in New York.
Yeah, we have a very similar situation. I'd say we have the utilities who both run the queue process and also do the distribution planning. We have a fairly controlled process where we have a very strict standard interconnection that goes through all the data that's required, dates for delivery of studies, specific timelines. And then we have distribution planning regulations that say when distribution plans have to move forward, what data they have to include, and it does explicitly call out the existing and queued resources beyond a certain stage. There's kind of best practices for how to include kind of the most certain resources and not necessarily concern yourself as much with the things that have just entered the queue. We go through these waves, so we want to make sure we're having the best view possible, and then we run some sensitivities on those. But all that is controlled through our tariff.
All right, great. And then Juan, if you want to speak from the utility perspective, really, and you obviously have a perspective on multiple states, so very curious on your take.
Yeah, and I think we do the same thing. It's following best practices, right? So and it's not only, let's say, data share, right? So especially these large DER, let's say you 5 megawatts, your large installations. We also have a standardized process in which they applied, and everybody's basically looking at the same application queue, right? And then more than that, they get to a stage where now it comes into the planning phase. And there now you not only have planning and distribution planning, you have a group, depending on the project, you have a group of engineers, right? And each one have their own phases of what to do at what stage, because it's not only the planning folks and the DER folks, there's also maybe relay coordination folks and substations folks involved. So we have the same thing, best practices. We have, depending on the stage of the application, various groups get involved. And then we use consistent platforms to basically share that information of the stage and the technical requirements and all that.
Okay, great. Thank you. Lisa, do you want to queue up a couple more Q&A questions from the audience?
Yes, I do. We have a question back to Jeff. Is there specific action that the North Carolina Utilities Commission has taken to enhance tax credit compliance for the interconnection process? Or is that a benefit of actions that the commission is taking otherwise?
Good question. So I think, 2 recent actions. I think, the commission approved this rollout of provisional service for state jurisdictional projects. And that was partially addressed to speed up the interconnection. And with that would have the side effect of increasing tax credit eligibility. But, they also, the commission recently approved a resource request for proposals for solar and storage, and really emphasized in that order that they're looking to maximize the quantity of resources that are eligible for that tax credit to ensure cost effectiveness. And so I think that the actions taken together, as well as, have been at least highlighted the commission's interest in this and really enabled it as well. So through that provisional service. And
Skylar, we have a lot of questions for you. I'll try to tick off a couple of them here. First, what, in your view, are the key factors that have enabled your success with the scale of DER growth and interconnection speed? Tools, regulatory support, and how do you ensure the utilities have the tools and resources they need to do this quickly?
I'd say without a doubt, it's the value of DER tariff. You know, when you have locational price signals and folks know what they're going to make beforehand, it really speeds up that whole process. You know, the values are pretty good. They're compensated quite well for doing that because they are providing quite a few benefits. And so having that market signal has been the biggest thing. But along with that, we did a lot in the late 2010s to try to remove barriers. We made the interconnection process more flexible. We did a number of things in terms of timeline reduction, as well as having incentive programs through our companion agency, NYSERDA, that pay incentives to these technologies as well. And so we had an extremely successful New York Sun program that was educating folks on permitting. We had a lot of permitting reform. We had the value of DER tariffs telling people where they should go. We were posting hosting capacity maps. So it was really all about that information sharing, because this is already a tough enough game to get anything interconnected and operational, even if you know all the information. But if you don't know, it gets exponentially harder. So it's really been that information provision that's been the most useful.
All right, one other question is about data centers and AI, and how are you incorporating the demands being forecasted for data centers and AI in your planning processes in connection with DER interconnection? How is that coming together?
Yeah, so unfortunately, I couldn't just say no thanks, but I would sometimes if I could. But what we are doing is trying to incorporate those into our long-term plans as well. You know, they're queued within either the New York ISO interconnection queue or our interconnection queues. And we are using the proactive planning process and the CGBP to identify where those are coming, what their likely impacts are going to be. They are much larger than average loads in many cases, but they're also not that certain. We've already had a number of projects turn over or shrink or double in size or withdraw entirely. And so we're having to run a lot of sensitivities along with those. But the main issue in New York State is that on the wholesale side of things, we haven't had as fast of renewable deployment as we wanted. And most of the interconnections of those large loads are happening at higher voltages. So they're not really impacting these DERs as much. In fact, the DERs are kind of saving us a little bit by maintaining their deployment while our large scale renewables have faltered, so they can actually keep providing that renewable energy for us.
All right, thanks. And how about one more question? This one for Juan. Folks are trying to understand a little bit better how you do the studies, the group studies. So how do you estimate the cost? How do you know, is it based on the queue? How do you estimate per region? How do you sort of create or group the regions? How did that all come around?
Sure, that's a great question. So it all starts with the queue actually. So we look at the queue of existing DERs that have applied, and we look at basically our entire area, right? And then from that queue of basically customers, then we zoomed into the makeup of our substation and distribution circuit, the lines, the feeders. And then there's natural connections, natural symmetry between some substations and others. So when the planners look at an area, they look at, okay, what substation back up, what substation, and that connection, that natural kind of boundary is what we use to kind of carve out basically substations within a group, right? So now you have the group of customers in the queue, and based on the actual on the distribution system itself, on the actual distribution system, then we carve out, let's say, substations, and then all the circuits that go with those substations. And that carve out is what I call a group. And then now that I have that group selected and I have these groups of substations, this group of lines, any customer that's connected to that group substation and those lines, then we study them together, and we study them on the various scenarios. But basically now we basically turn them all on, and we do the study assuming they're all connected, and we identify which violations come up after that. And then we plan for those violations. We do the upgrades, and like I mentioned before, we take into account maybe a scenario where with the addition infrastructure, what's the best way to maybe improve reliability at the same time. So we do those studies, we do that potential solution, and then we develop costs for those solutions. And then those costs, we engineer the solutions, develop costs, and then those costs are the ones that are used to basically develop a cost per kilowatt for the current customers and the future customer, because after the solution, now we can identify, okay, how much DER capacity my system has now, and then with those reinforcements, how much DER capacity do I have after? And then that delta is what gets divided by, the DERs now and the DERs in the future to put a cost per kilowatt.
That's great. All right, thank you. We have more questions, but Catherine, I think you have as well.
Yeah, thank you. So I'm going to launch a poll. I'm going to take one of those last questions in the last round that was focused on evaluating grid benefits and costs, and we'll focus on that for a moment. So launching the poll question, please go ahead and put in your response there. There's also an opportunity to write your response into the chat box if it doesn't fall under one of these options. And so this question and this section kind of focuses on how DER technologies, we know, provide a range of benefits to the electricity system, but they may also pose some costs that vary depending on technology type, location, and capacity. And so there's a range of programs that can help evaluate DER benefits and costs and improve by creating DER operation profiles and dispatch schedules, evaluating DER benefits and costs through programs, rate design, planning processes, such as DER rebate programs, net metering, non-wires alternatives. So I'll give 5 more seconds and let a couple of other people respond. Thanks so much for participating in this poll. All right, so I ended the poll and we'll share results. So we see of the types of programs, rates, and processes across the states from our audience, 0% responded to DER rebate programs. The most responded net metering as a program, 43%. Time-varying rates was a close second, followed with a tie with proactive grid investments for hosting capacity and assessment of DER's non-res alternatives. Let's see. So we have now a question. Thanks so much for participating in that poll. I will turn to our panelists to also give their take on how your utility or state evaluates grid benefits and costs of DER. I'll go first to Juan, if you want to respond to that question.
Yeah, and I think I'll take it from the point of what I've covered so far, which is how did working with the regulators and stakeholders, we were able to allocate benefits and costs as we do DER studies, right? So I'll take it from that end, and basically, it falls to what I mentioned before. So it's not that we only have a DER goal; we also have our greenhouse gas emission goals, right? Mandated, let's say, by the state. And with that, you're going to have load growth in the system as well, right? So it's looking beyond the now and looking into the future, how we were able to evaluate the benefit to the grid by doing reinforcements for DER now. So if we plot the growth that would result from electrification, right? Obviously, in the future, we will need investments, we will need reinforcements in order to accommodate the electrification, right? But right now, we have a need right now for DER that wants to interconnect in certain areas, right? And, but the need is now. So do I wait for the future for them to interconnect? Or do we realize there's benefit here, there's immediate benefits, and there's future benefits for both, right? And then by realizing that, now we can say, okay, let's allocate costs. Let's include the benefit to distribution customers in the future as part of greenhouse gas emissions into the current basically construct. And taking it from that end is one way that as a utility, as a state, we've been able to evaluate benefits to the grid, to the distribution customers by enabling DER.
Awesome, thank you so much. Let's go to Skylar in New York. I know there's a lot of different options of programs. If you could pick your top evaluation for cost or benefits.
Yeah, sure. So we've done the two big ones are the New York Sun program, which has just achieved its ultimate goal of 6 gigawatts of storage through 2025. They already have enough money and projects signed up to go all the way to 10 gigawatts. And that money was based on a number of studies that showed the benefit of having, distributed solar from not just the GHG perspective, but health impacts, grid impacts. And that ties in with the second component, which is the value of DER tariff. Having that market signal that's able to pay these developers, anybody that comes online can access that tariff and maintain that revenue stream has been phenomenally beneficial. But I don't want it to seem like we just came up with this and it was a piece of cake and now it's the best thing ever. It took us probably 2 or 3 years to come up with that. And it was brutal and it was difficult and it took forever. And there was a ton of stakeholder engagement, report after report after report, study after study, figuring out the best way to do things, whether it's zonal or nodal pricing, whether it's real time or day ahead pricing, whether there should be discounts for the ICAP rating, whether we should give a full E value or some fractional value of a REC, whether we need to give everybody distribution relief value or just a specialized component that we study for every individual project. How long do you guarantee those revenue payments for? All of these decisions had to be made, and we made our decisions on how we do those, and we have white papers on each one of those decisions. I would encourage anybody who's really interested in trying to create their own compensation mechanism for DER that's kind of a standalone tariff mechanism. Please read those, save yourself years of pain and suffering, and learn from all the tears shed in New York State and all the difficult stuff that we had to do, because that has been, once we got that right, it's been 5 or 6 years of just constant deployment.
Really appreciate that nuance to share the process and history that's gone into it. It's easy to look at what's going on in New York now and without seeing all the iceberg underneath the surface.
Right.
So Jeff, turning to you, any lessons learned from North Carolina as you've implemented some of your programs?
Sure, yeah, and we have almost every one of those programs, from rebates to rooftop solar and batteries, the time of use rates and critical peak pricing. And a lot of what underlies, the big question often when we get these types of programs is how much should the incentive be? How much should people be paid to discharge a battery or to put solar on the roof or to participate in demand response? And the commission here in North Carolina is largely focused on avoided energy and capacity as the two primary categories of benefits that kind of get included when you look at these direct incentive programs that the utility participates in. And so that obviously is, that benefit we've seen in past proceedings, how some have argued that benefit is not enough and doesn't cover certain other benefits. And while that may or may not be true, the commission in this state has decided that the energy and capacity is the largest component. But at the same time, we also look at a lot of DRs that are going up on the grid, battery microgrids and things like that. And we look at, what would it cost the utility to build the same resource? And in some cases, we've actually increased the capacity or the energy, avoided capacity or energy cost by kind of a proxy value, recognizing that we do have state law that's pushing us to carbon neutrality by 2050. And so the avoided system cost today may not be enough to reflect the value of, energy efficiency or clean energy generated tomorrow. And so there's been a lot of work on that, and we're in the midst of a lot of program design that kind of will roll out DR to non-residential customers. Might be a very large impact on the system, and that's been a big focus on it. But the commission here is really asked to focus on the energy capacity and those kind of quantifiable and measurable benefits.
Thanks so much for sharing that. So let's pivot to flexible interconnection. I'm going to launch a poll question to the audience on whether your state offers flexible interconnection. And just by way of introduction, flexible interconnection procedures can reduce DER interconnection costs in exchange for curtailment under specified grid constraints. So giving folks just a minute to answer this poll, and then we'll turn to our panelists to answer this. All right. I'm going to go ahead and end the poll and share results. So we have 23% yes, your state offers flexible interconnection, 33% no, and 43% is I don't know. So thank you so much for responding. I'll just turn to our panelist. So one question is how your state is evaluating and advancing flexible interconnection and or your utility. What's the uptake so far and how do you see implementation evolving? We'll go with Skylar.
Sure. So we don't have like a fully baked flexible interconnection pathway right now, and that's primarily because we've had a fairly flexible interconnection process to begin with through the various attachments to our interconnection procedures that we've allowed to happen. People are already able to choose kind of their interconnection limits and kind of, especially with storage, their discharge and charging limitations that they want to propose to minimize their interconnection costs. But as we get more and more of our locations in New York State reaching their hosting capacity, we want to make every effort to maximize, the interconnection that we have available to us, and minimize those costs. So we're advancing a couple of different things for flexible interconnection. One is the more traditional, where things like solar will have an agreement with the utility to say, in those extreme circumstances when potentially there's low load and we'd be injecting and you need to, we would have needed to upgrade this whole system to allow injection during that worst case hour. You can just curtail us by a little bit to make sure that never happens. And so that kind of flexibility accounts for those real-time variations by having kind of a static agreement with the utility and the developer to do that. We're also considering things like a two-phase approach that allows developers to install different technologies, such as like another small storage asset to manage those types of situations and enter those into the interconnection agreement to make sure that the issues that would have caused higher cost interconnections are now managed through this other technology operation. They can kind of put algorithmic controls on those assets.
Very interesting. I'll go next to Jeff if you want to share perspective on where you are at.
Sure, yeah, and as described before, it is kind of an early journey in flexible interconnection. It hasn't been a very utilized process, but to date, it's largely been utilized for transmission projects that have very long lead time transmission upgrades and trying to get connected a little bit earlier, and so that's one option that's been available, but we do have been improving our study process to at least allow for interconnection operating agreements to limit the amount of output. So if someone wants to add a battery to capture some of their output and reduce their export to reduce the impact on the system, they can do that. But again, one of the big problems there is just, since we don't compensate for curtailment, there's a lot of risk on the developer to take that stance. And a lot of times the provisional or the e-risk studies will give them you can only operate at 50% for this entire season because that was the worst case scenario. Rather, they don't have the capability right now to dispatch these generators, up and down as needed to respond to transmission or distribution constraints. So that's a key, I think, enabling technology. But on the distribution grid, we haven't seen a lot of massive upgrades or untimely interconnection, and so most of those just kind of proceed as normal, and they don't need to necessarily rely on that flexible interconnection.
That's very interesting. Thank you. Last but not least, Juan, if you want to share from the utility perspective, really important perspective to share here. Thanks.
Yep, and similar to what's been said already, well, we do have flexible interconnection already. We have what I'm going to call it. My preferred way of calling it is planned flexible interconnection. So it's that fixed, value that we can tell a developer, okay, if you curtail to this amount, but it's a fixed amount, right? So they have the ability now to downsize the export capability, right, in order to interconnect to avoid any upgrades that will be necessary otherwise. So that's already there. We've been doing that for a while, and a lot of DER customers have taken advantage of that. The next phase, which we started recently, is a time schedule, right? So we're now allowing DR connections to have, because that fixed value rises through the whole year, but that that doesn't benefit, let's say, storage. So now we do have a time schedule in which we break down the year by seasons, right? And we can say, during this time you can export at this much, during this time you can export at that much. and that gives them more flexibility, more ability, you know, to make their project work, let's say. So we have that already. Flexible interconnection it's happening here. The next phase of flexible interconnection is what I like calling like on-demand flexible interconnection, right? And that's the, and by the way, as a planner, we consider flexible interconnection another tool in the toolbox, right? That's what it is. If we're able to use it properly, it is another valuable tool in the toolbox. But what do we need to do with that? You know, we're able to, in order to count for flexible interconnection, we need to be able to see it, right? We need to be able to control it, and then we need to be able to count on it. So right now, I think we're also at the early stages in which we're trying to get the technology out there that allows us to see it, that allows us to control it. And then once we have that information and we've been able to do that for a while, then the next phase is to identify how much can we count on it. And once we have those three things, I think, you know, we'll find that flexible interconnection, again, is another tool, valuable tool in the toolbox that we can use to plan the system in the future.
Amazing. Thank you so much. And I know we're at time, so I wanted to thank our esteemed panelists for your excellent presentations and engagement, and thank you to our audience. I have a couple of quick slides to share with additional resources. Just give me one moment. All right. Are you seeing my screen now? Yeah. So we have an exciting couple of webinars coming up. So part 2 in our promoting economic efficiency and interconnection, we have a webinar focused on cost sharing that'll be taking place on September 29th next month, followed by our final webinar in the series, which will focus on maintaining a reliable, resilient, and secure grid in the November-December timeline. So visit our i2X website for slides and recordings of this webinar and past webinars. You can also use this QR code if you're interested in learning more about the DOE Distributed Energy Resource Interconnection Roadmap. There is also a roadmap focused on transmission level solutions. So with that, I will stop sharing. Thank you again, and thank you to the DOE i2X for your support. Really great discussion today.
Thank you.
Thanks.
Thank you.